Hey guys, so in this video we're going to discuss a way to express the ratio of reactant and product in a reaction mixture at any point during the course of a reaction. Consider a general chemical reaction where reactants A and B form products C and D with their respective coefficients. Now at chemical equilibrium, we can express the equilibrium constant in terms of equilibrium concentrations Kc or equilibrium partial pressure Kp. However, if the reaction has not yet reached equilibrium or has been disturbed from its equilibrium, the reaction quotient Q is a good value to gauge the progress of the chemical reaction. The reaction quotient expression can be expressed in terms of concentration or partial pressure, just like the equilibrium constant. However, unlike the equilibrium constant K, the reaction quotient measures the extent of the reaction at any point of the reaction. Therefore, the concentrations or partial pressures of the reaction components are not necessarily at equilibrium. The reaction quotient depends on the current state of the reaction. Therefore, Q can have many different values as the reaction proceeds. For example, if only reactants are present in the reaction mixture, Q is equal to 0. This is because Q is equal to products over reactants, and if you have 0 products, then your numerator is 0, causing your overall Q value to be 0. Now, if the reaction mixture only contains products, then Q is actually equal to infinity. This is because you have a 0 on the denominator of your Q fraction. And finally, if all the concentrations of reactants and products are equal to 1, then Q is equal to 1. Now, the progress of a reaction towards equilibrium can be determined when the reaction quotient is compared to the equilibrium constant. So the blue line on this graph actually depicts the progress of the reaction A forming B, while the red line indicates the equilibrium constant for the chemical reaction at this temperature. We can see that at the point of intersection of the red line and the blue line, Q is equal to K. So that means that these reactant and product concentrations, the system is at chemical equilibrium. However, in the case when Q does not equal K, Q may be less than or greater than K. Comparing the reaction quotient Q to the equilibrium constant K informs chemists about the direction the reaction must proceed in order to reach chemical equilibrium. To elaborate, when Q is less than K, this indicates that in the current state of the reaction, the ratio of product to reactant concentration is lower than the equilibrium concentration ratio of product to reactant. Therefore, in order to reach equilibrium, the reaction must shift to the right towards the products, and the forward reaction dominates. Now, once the ratio of product to reactant is equivalent to the equilibrium constant, the chemical system is at dynamic equilibrium. And finally, when Q is greater than K, this indicates that in the current state of the reaction, the ratio of product to reactant concentration is higher than the equilibrium concentration of product to reactant. So, in order to reach chemical equilibrium, the reaction will shift to the left towards the reactants in order to lower the ratio, and the reverse reaction dominates. Now let's consider the following problem. It states that a reaction mixture contains NO2 concentration that is equal to 0.0255 molar and N2O4, which is equal to 0.0331 molar. We're supposed to calculate the Q, which is the reaction quotient, and determine the direction in which the reaction will proceed. Now we can see the chemical reaction that N2O4 gas forms 2 moles of NO2 gas, and we're given the equilibrium constant Kc equal to 5.85 times 10 to the negative third. So first we're going to determine the reaction quotient, Qc, and then we're going to compare the value that we calculate to the equilibrium constant in order to determine which way the reaction proceeds. So remember that Qc is simply expressed as products raised to their coefficients over the reactants raised to their coefficients. So in this case, Qc is going to be equal to NO2 squared over N2O4. So if we plug in the concentrations that are given to us in the problem, we can solve for the value of Q and get that it is equal to 0.0196 at this point in the reaction. Now, in order to compare our reaction quotient and our equilibrium constant in this case, it may be easier to write our reaction quotient in terms of scientific notation. So this is actually equivalent to 1.96 times 10 to the negative second. Now this allows us to determine that QC is greater than our equilibrium constant value, 5.85 times 10 to the negative third. Now remember, if QC is greater, this means that our fraction of products over reactants, we actually have more products present in the reaction mixture, and therefore we're going to need to shift in the opposite direction to form more reactants, and therefore the reverse reaction is favored. So overall in this video, we were able to define the reaction quotient and understand that as the measurement of the extent of a reaction. The reaction quotient is differentiated from the equilibrium constant because the reaction quotient does not necessarily have to be at equilibrium concentrations of the reactants and products. Finally, we learned that if we can compare the reaction quotient to the equilibrium constant, we can determine which way the reaction will proceed in order for the reaction to reach equilibrium.